The last time, we were talking about Krull dimension, right? So Krull. Chain. Primes. And we start counting zero. We say this has length in. And so the Krull dimension, when I refer to the dimension of a ring, my default will always be Krull dimension. There's other notions of dimension that may come up later, but this consider Krull dimension, from my perspective, is the top of the hill. Is a premium over the lengths of chain primes in R. And I'll often write this as MR. So some examples we had last time. R is a field or finite. Then and you all totally copied that on homework 2, I guess. Example. If Noetherian. I'm not going to prove the statement, I'll just give it to you. And I'm going to guess this. Too big. Maybe the easiest thing to think of, my favorite Noetherian domain is a field. And what would the answer be if this were a field? Okay, what's that? We're going to see sort of how this works after a bit. Notice all the examples that I've given you have finite Krull dimensions. Can anybody give an example of a domain that has infinite Krull dimensions?
Sure. An example X involve splitting pies, I think, in some.
Take a field and infinitely many variables of all the memory.
Right. I mean, certainly you could do that, right? I mean, if you suppose you have a field, right, and you do this. Then you certainly have the chain of primes 0 inside x1, inside x1, x2, inside x1, x2, x3. You got infinitely many variables, so stop, right? Everybody okay with that? So just to show you how weird this can get, and because I did weird things. So Krull dimensions how high you can stack the prime ideals, loosely speaking, right? Is this one countable? What's that? Yeah. One would think, right? but it's not. I can give you an uncountable chain of primes in that. In fact, just to make you angry, I'm gonna do this over the field of two elements, right? Doesn't get any smaller than that. I claim that there is an infinite chain, an uncountably long infinite chain of primes in there. I mean, there's obviously a countable one, right? Just like this. Everybody agree with that? So there's certainly a countable chain. How would you do one that's not? So, watch this. Thing do. Consider there's a bijection of sets from the natural numbers to positive rationals. Everybody go over that. And this map of sets induces an isomorphism. Let's say F bar from two yeah, shoot. Everybody okay? So whatever this, and so this takes into whatever positive rational, it just works this way, right? This is a isomorphism of rings. In this context, it's easier for me to show you what the prime ideals are. Notice that if you have any subset of variables, right, whatever these subset of variables are, that subset of variables generates a prime ideal, right? X, I1, X, I2, X, however much you want this to generate a prime ideal. Because when you quotient out, it's essentially killing the variables, and it's just a smaller polynomial ring, if you will, over a domain, so it's still a domain. Let us let gamma be in the positive reals define T gamma is equal, is the ideal generated by the set X beta, where beta is greater than gamma. It's like a dedicated cut, right? Notice that if gamma 1 is less than gamma 2, then P gamma 1 is contained in P gamma 2. And my bad. That's what I meant, beta less than gamma. But otherwise, I'd have to reverse this, right? If gamma 1 is less than gamma 2, then P gamma 1 is contained in P gamma 2. And each P gamma, right? I guess it's just generated by those variables, right? This gives a chain of times. And it's uncountable. So there's your uncountable chain of primes in this ring. Whatever these are, just pull this back here, and I'll give you your. Notice it's much harder to write down here than it is here, right?
Can we get even higher cardinality, or is this the best, or best, but
This would be the best for the particular example that I gave you. Right, and which is kind of crazy, right? Because this ring, and this is the dramatic, and this ring is countable. Now, of course, if you have an infinite countable set, then there are uncountably many subsets, but, you know, you don't expect most of those subsets to be ideals, but here there are enough, right? There's uncountably many, in fact, prime ideals here. Okay, any questions? Okay, so here's another one. Next question, um, here's another question for you. If R is Noetherian, is the dimension of R finite? Now, this is a natural question to ask, right? Because what does it mean to be Noetherian? One of the equivalent conditions is that if you have any stack of ideals, prime or not, it must stabilize, right? Does this put a lid on? Okay, put your money where your mouth is. You think not?
You've shown me this before.
Oh, okay. Um. Well, how about the converse? So if R is Noetherian, it's the dimension of the finite. No. If. How about the other way? If you have a finite dimensional ring, is it Noetherian? This is awesome. Let's discuss how we would get examples for both of this. I'm not going to, the first one is actually, I think, a little bit tougher. Can anybody give, an example? In fact, let me go crazy here. Somebody give me an example of a zero dimensional ring that is not Noetherian. Not zero dimensional, right? Make it zero dimensional. I claim, I'm gonna call this R. R is quasilocal. Zero dimensional. Not Noetherian.
The Macquarie community are generated by all X1, X2, X3.
Yeah, that's right. So let's go through this. Why is it, well, okay, well, I don't know, answer any of these, because once, except for the non-Noetherian thing, I think they kind of build off each other. Why is this zero dimensional? Let P and R be prime ideal. Okay. Then, um, put it this way, as zero is in P and xi squared is equal to zero. Here I'm abusing the notation here. The xi's are polynomials from the original, or polynomial variables from the original ring before I get the quotient. But I'm gonna, when I say xi there, I mean xi plus this ideal that I modded out by that code set. So I'm abusing the notation. Therefore, each xi is in P. Alright. So, P contains right. But this is a maximal ideal, right? The ideal x1 squared, x2 squared. Writing it out more formally this way, this is actually maximal ideal. And you can see that because when you mod out, you just get the field, right? So P is the unique prime ideal of R. And that answers both of those first two questions. It's unique, so it's quasi-local, and there's only one of them, so it's zero dimensional. Right. In fact, you can think of this, I like to think of this as this generated over F by countably many nilpotent, square nilpotent variables.
Or not Noetherian, we still get that chain X1, X1, X2.
That's right, but you still get. That's exactly right. But it's not Noetherian. Because we still have the chain X1 contained in X1, X2, contained in X1, X2, X3, etc. Right, and it's an easy computation to show. For example, X2 is not in the ideal generated by X1 and so forth. Notice that, again, this is kind of a cool ring because everything in this ring is either a unit or a nilpotent. Okay, so there's a pretty extreme example, or that's a pretty extreme example to tell us no for the second question, because we've got a zero dimensional ring, it's not Noetherian. How about the first one? Can somebody give me an example of an infinite dimensional ring that is Noetherian? Well, the thing that kind of messes with your head a little bit on this, I think, is you can't stack in a Noetherian ring. You never have like an infinite stack of ideals. So how in the world could you have an infinite stack of prime ideals? And the answer is you can't.
You don't have a larger stack.
But that's the deal. What you do is you can never have an infinite stack of primes because that would violate the Noetherianism. What you can do is build your buildings taller and taller. right? Suppose you've got a stack of one, then a stack of two, then a stack of three, and a stack of four, and so forth. And suppose that there's no limit to what you could do here. Now, how can you do this and also keep things Noetherian?
Fine splitting thing.
Yeah, so here, this example is due to Nagata. I'm not gonna go through the details, but what I hope to do is give you like a good intuitive feeling for why this is true. So the idea is you want to build higher and higher stacks of primes, right? And you can never build an infinite stack because then it won't be Noetherian. That will be a big violation there. So how do you do it? Well, here's Nagata's strategy. Start with a field. Now, here's why I'm indexing polynomial variables this way. I want this to be my stack of one. I want this to be my stack of two. I want this to be my three high stack, et cetera, et cetera. But of course, one problem, if I just do this, I mean, it's certainly true that, look, this prime is one high, this one is two high, right? X1 up to X. This one's three high, 3, 1, 3, 2, 3, 3, and so forth. Why can't I just quit there?
It's not.
Right? That's a problem, right? There's infinitely many variables. It's not Noetherian, right? And also, the buildings aren't independent, right? Because this guy, X11, could also be the first floor to this guy, right? So you could slide this over here. That's problematic as well. So what do you do? See how I put those things in parentheses? What I want to do is I want to make those the only maximal primes in a chain. So check this out. Let S equal if I call this P1, P2, P3, N, really what I've done is this is the union PK. Uh, So I want to take that union of primes and I want to make the multiplicative subset that is the complement of that. Right? So in other words, take everything that's not in the union of these primes. For example, X11 plus X21 is not in the union of these primes because that thing is neither here, there, or anywhere else. And so X11 plus X21 becomes a unit, right? And really, once you do this, if you call this originally R, Using the notation, okay? And then it's this stack here. X31, X31, X32, X31, X32, X33. Done here. And more generally, we have the stack XM1, XM1, XM2, XM1, XM2, XM3. Actually, I could have started all these at 0, but actually looking back on it, I'm glad I didn't. 1, XM2. So I think we would all have to agree that the dimension, the Krull dimension of this is not finite, right? Because I've got a stack of length n for every n. So the supremum of that's going to be infinity, right? Well, that's Noetherian.
The primary deal of RS should live in the union of the PA, right?
So in particular, any prime ideal in that localization is finitely generated. That's a super trick right there, right? That's kind of the thing, because every one of these primes in the union, there's no upper bound to the number of generators, but every single one of those primes is in fact finitely generated. And so that persists into the localization, and so there you go, right? So now R localized at S is Noetherian because all of its prime ideals are finitely generated. So this is an incredibly clever example due to Nagata that shows that you can indeed have rings of Krull dimension, the infinite Krull dimension that are still Noetherian. Okay. All right. Any questions on that? So here's a question. So here's a motivating question for what we're going to look at now that I've, polluted your head with all these examples here. So here's kind of a motivating question, Suppose, suppose you have R, some commutative ring of identity, and you know this Krull dimension is n. What can be said you said about the Krull dimension of R power or RS? And while I'm at it, for the power, right? You said about that as well. Well, let me make a mark here. Where am I? Suppose P from R P is surjective homomorphism. So, again, R and T are community identity. What do you suppose you could say about The Krull mentioned these two, if anything.
Mention T is less than equal to R.
Yeah, you got it right. Krull mentioned, these, the Krull are, somebody explain why.
Correspondence theorem.
Yeah, it's the correspondence theorem, really. So if, let's say P0, P1, Pn, is a thing prime in P, then uh, in R, right? And how do I know they're distinct?
It's a certain-
Well, I mean, it's the correspondence theorem, right? So these are distinct chains. So these correspond to, in fact, perhaps I should write this way. Let me do this way, it might be clearer. Then each EI corresponds to UI mod I with I equal right? From this theorem, we obtain a chain of prime in R of length at least n. So for every chain of primes of length n and t, you can find a chain of primes of length n and R. And so that gives the desired equality, right? What happens if you have, what happens if instead of surjective, you have injective? You were right to say nothing, because that's kind of what happened, right? I don't expect an inequality in either direction, right? Because you can have a large dimensional ring and you can embed it into its quotient field, right? So this might have dimension n, and the quotient field will have dimension 0. On the other hand, this could be a field, and you can embed it into a polynomial ring over that field and uncountable many variables, right? And so I don't expect any inequality to hold here if B is replaced by an injective polynomial. Agree? What about polynomial rings? And actually, this was what inspired me, because oftentimes this would relate, right, in the following sense. If you have R, and then you might have a homomorphism. So R is a subring of R of X, And R of X, will map surjectively on something like this. And in some cases, you might consider this, if this, homomorphism is the identity on R, then this thing might be a ring extension of R. And the answer to this question gives you sort of a bound on that, right? So what can we say? Anybody want to take a guess? To either one. So suppose lower bound, upper bound. That we had. If I wrote in there, that would certainly be true, but you do a little better. Plus one. And plus one. And we'll see why this is true. The upper bound's a little bit more elusive. I don't know about 2 minutes. And actually, there have been examples produced to show that this can reach 2n plus 1. I think that they even done a proof of it. So let's start down this road. So the first thing we're going to do is we're going to look at polynomials. So I am going to establish this fact that if you have a ring of Krull dimension n, and its polynomial ring has a Krull dimension at least n plus 1 and no more than 2n plus 1. I want you to put on your aluminum coated hats and pay attention while I do this, because I want you to be skeptical about, ask yourself this as we go along. Every step that I do for polynomials, ask yourself, is this going to work for power series as well? Okay, so let me get warmed up here with the following proposition. Well, actually, I'll do this. So I always freak out, and go outside my notes, but I'm gonna do this first, just to establish this. Yeah. Okay, let's do this part. Maybe. Uh, Anybody know how to do this? There's actually probably multiple ways to skin this cat, but there's one that I think is probably the easiest. Let's start here. Suppose P0, P1, Pn is a chain of prime. Somebody describe to me how I can get a chain of primes in Rx. Right, but I mean, so these are sets, these are subsets of R. What's the corresponding chain that I would maybe want in Rx?
All of X, one of X.
Okay, so I can certainly do this. Now, these are all prime ideals, and this harkens back to our days looking first at polynomial rings, because if you look at Rx mod PIX, this is isomorphic to R mod PIX. And so since PI is prime, that's a domain. So polynomial over domain is a domain. So that means that this is a prime. So these are all primes. They're distinct because the PIs are, right? So now I've got a chain of linked in upstairs, the polynomial ring, and how do I squeeze a little bit more juice out of this turnip?
At the ideal term right by X.
You're close. You need Pn in X. Right, because the ideal generated by X may not contain it, yeah. And of course, the quotient here is just R mod Pn, right, which again is domain. This one, in fact, well, no, sorry, if Pn is maximal, this one's maximal, Pn may not be maximal. So there is a chain of length n plus one. So whenever you got a chain of length n, you've got a chain one longer upstairs, and so that means the Krull dimension has to be at least n plus one. Right? Okay, well, that was, as you might expect, the easier bit of what we have to do. I need to develop a little bit of junk to figure out the rest of it. Proposition. Um, In fact, one of the things that I'm gonna do to kind of prove the upper bound is I'm gonna reduce the problem. And so I'm gonna give you some results here that help us reduce. But R be a domain. So now this obviously applies to interval domains. The quotient field. So R is a domain quotient field K, and X is an indeterminate, then there is a one-to-one correspondence. One-to-one correspondence between ideals of Rx that contract to zero in R and prime ideals of Kx. Primes of Rx contracting to zero in R and primes of Kx. So let's discuss how this works. Let me, I hope give you kind of an intuitive feel for why this should work first before we really get hardcore with it. What does it mean for there to be a prime of Rx that contracts to zero? That means that that prime ideal, whatever it looks like, has no constants in it, right? No constants. And so I can take that prime and localize it up to Kx, right? And it should still be a prime. And again, it's another correspondence thing. So let's let gamma R of X a prime contracting to zero. That is to say, gamma intersect R zero. So there's no constants floating around in this thing, right? Let's let S, so I'm gonna look at specific multiplicatively close set. Let S be the set of elements in R that are not zero. Since R is an integral domain, this is a multiplicatively closed set. Notice that gamma, because it contracts to zero, misses this set. So if I look at gamma S, that is all things from gamma divided by ohms of R, this is a proper prime ideal of So given one of these ideals that contracts to zero, it corresponds to its localization, which is going to be a prime ideal of KX. On the other hand, also, if A in KX prime, then A intersect RX, which I will call gamma, prime in RX and contracts to zero in R. Why does it contract to zero in R? Well, it has to, because otherwise gamma contains a constant. And if gamma contains a constant, well, I should say a non-zero constant, then A contains a non-zero constant. And that's impossible because it's a proper prime ideal. Anything that contains a constant, since we're over a field, that ideal will be the unit ideal. And notice sorry, correspondence. Because if you take this gamma and you localize it back, you'll get the original A. That's an easy computation to see. Okay. Any questions so far? Okay, all right. Here's the gut check. Let me ask you all this. So far, Proposition 442, does it, work for power series? And if so, what's the problem? Or if not, I should say, what's the problem? Well, let me get you all ready for November 5th. I want to get the youth of our country all used up to go out and vote. How many of you think this works for power series? How many think it does not? Okay. How many are undecided? We need to send you to Latrobe, Pennsylvania or something so you can figure things out. It does not work in power series. Anybody know why? Anybody know where?
Localization stuff may be suspicious.
Yes, you should definitely be suspicious of this. This works for polynomials because what this equality says here, if I have a polynomial divided by an element from the ring, that distributes out. And certainly this is contained in this.
You can't factor.
For power series, this almost never works. Almost never.
I can't see
So
it.
what is true, so here is kind of the first bit of trouble that we run into if we wanted to go further. For power series, what is always true, and let me just say over a domain. This is always true because what's over here is a power series over a single denominator, and you can just put that denominator all the way across this here. What you have here is complete freedom on your choices. For polynomials, this is not such an issue because there's only finitely many terms that you can collect to a common denominator. Here, it's problematic. In fact, I'll tell you how bad this is usually. Usually, if you look at the quotient field of this and the quotient field of this, not only are they usually not the same quotient field, but the quotient field here has infinite transcendence degree over this one. That's how much bigger it is, right? So this almost never works in power series. All right, we will go further next time. Any questions? All right, well, I will see you all on Wednesday.